we open circuited the high voltage winding, and we have connected the supply to the low voltage winding. So wherever you are connecting the supply, that is considered as primary winding, and the other thing is secondary winding where your load is connected. Okay, so in this experiment, you are going to measure three things. One is the voltage, another is the current, and another is the power. So the power which you are measuring is going to give the core loss of the transformer. Then the voltage. So what we need to do, we have to change this auto transformer variable applying rated voltage across the transformer low voltage winding. Okay, already I told why we are open circuiting the high voltage winding. In high voltage winding, if you want to transform, then if it is a if it is a 11 kV or 765 kV transformer, it is sufficient to have 11 voltage source in your side. So for testing this transformer, only for the testing purpose, you don't need to have 765 kilovolt. So with the low voltage itself, you can test the open circuit test of the transformer. So sufficient to have a lesser voltage of source. Then what you are doing, you are bringing it to the 230 volt. Then you are just measuring the current, voltage, and power. So whichever the power which is consumed now, that will be giving the core loss, because there is no power consumed in the load side because the secondary terminals are open circuited. Secondary terminals are open circuited. So now in this short circuit test, what we are going to do is we are going to short circuit the low voltage winding, and we are going to give the source to the high voltage winding. Okay, similar procedure. Only thing is here the transformer we are keeping it zero. Initial position it is at 0 volt. Then what we will do is we will increase the voltage from zero to some value. That value, that voltage will be rated current through this meter. Okay, so what we are doing, we are short circuiting the secondary terminal. Here we are short circuiting the low voltage terminal. Then after we short circuit, what we are doing, this auto transformer, we are varying from zero to some value. Till how long we are varying, we will be varying in such a way that we get rated current of the transformer in this ammeter. And once you get the rated current in this ammeter, we measure the voltage, then measure the current and measure the power. So this power, which is measured, is giving the copper loss, which is measured is giving copper loss. This is giving the current, and this is giving the short circuit voltage. So three things can also be measuring: voltage, current, power through that path. Then you are going to measure the. Okay. Now
Excuse me, sir. Sir, your voice is not clear.
Just a minute. My network is poor. Wait for a few minutes. Am I audible now?
Yes, sir.
Whether my screen is visible properly?
Oh, yes, sir, it's
Yes,
fine.
yes, yes. Fine, thank you. Okay, so in short circuit test, what we are going to do is we are short circuiting the low voltage winding and we are going to give the supply to the high voltage winding. So in why we are giving supply to the high voltage winding and why we are short circuiting the low voltage winding is, you know that if you are having a low voltage winding, the voltage will be lower in that low voltage winding and the current will be higher. The current will be higher and the voltage will be lower. In a high voltage winding, you will be getting high voltage and lesser current. Right. Now, if you are giving supply to the high voltage winding, you can allow the rated current to flow without giving more current to the low voltage winding directly. So if you want to give 13.6 ampere on this side, obviously on the high voltage winding, the current flowing through that will be higher. Okay, because that's why your transformer is operating at constant power mode. So when it is operating the constant power, because you know that the power and frequency will be constant, so when the power and frequency is constant, then the voltage and current will vary. So in the high voltage winding, if the current is in the high voltage winding, if there is some x current, then in the low voltage winding you will be getting more current than the x, right? So in that case, here if you are giving supply to the high voltage winding, it is sufficient to give lesser amount of current in the high voltage winding rather than more current on the low voltage winding. Why the low voltage winding will be carrying more current? Because the transformer is operating at constant power. So if the primary power is V into I, then the secondary power is equal to V2 into I2. So here in the low voltage winding, the voltage is lesser and the current is higher. So in this case, in the high voltage winding, the voltage will be higher, then the current will be lesser. So here also, like the low voltage, like the open circuit test, where we required only lesser voltage in order to give supply to the low voltage winding. So in the similar case here, what we are doing, we are able to give. It is sufficient for us to supply only lesser amount of current in order to give the in order to do the short circuit test. Okay, so with the if you are giving lesser current, then you need a lesser capacity of the power source. So here it is recommended to use high voltage winding to be connected to the source for performing the short circuit test. So in short circuit test, we are measuring three parameters: voltage, current, and power. So that power is going to give the copper loss. So from that power loss, what we are going to do is, So here the resistance can be obtained by P divided by I square. You know that P is equal to I square R. This you know. Then if you just rearrange this equation, you will be getting P divided by I square. So same thing from this system or from this circuit, we are going to obtain this R by based on power and current. So that is given by RO1. This is R01. So this is nothing but series resistance. So in this, actually in the equivalent resistance, we are finding this detail. Actually, we are finding, okay, this is R01. So actually, it should be like this. So this is R01 and X01. So whatever the value we are measuring, all the parameters are here. This includes primary plus secondary resistance, and this also includes primary plus secondary. We cannot find the values individually. Whatever the values we are finding based on this short circuit test, we are finding the overall value which includes both primary and secondary. We cannot segregate it. It is commonly acceptable that both the values will be same, means primary side value and secondary side value will be same. So you can consider like the primary will be R01 divided by 2 and the secondary value will be X01 divided by 2. So this is for primary resistance and this is for primary reactance. The primary reactance and secondary reactance will be equal, so we can consider that it is X01 divided by 2. So we have obtained this R01. So once you know Z is equal to R plus JX, you know that. So if you want to find the magnitude of this, Z is equal to R square plus X square. This you know. So you just rearrange this equation. So in such a way that you know R, you want to find X, and you know Z. Okay. So once you know this, so you just rearrange this equation. Just once you rearrange this equation, you can obtain the X. Okay, so X can be obtained using this equation. How we can find the Z? Z can be given by V divided by I. This is a AC circuit. Since it is AC circuit, V divided by I will be giving this Z. Okay, now what we have obtained? We have obtained this R01 and XSC. So from this, we have found this. From the open circuit test and short circuit test, we have obtained this shunt elements. This is RC and XM. So these two things we obtained using open circuit test. So these two values we'll be using for our further things. So with this, what we are going to do is, from this we know the copper loss, and from the open circuit test we know the core loss. So that we can implement this in the efficiency equation. So this is the overall efficiency equation by open circuit test and short circuit test. What we did is we obtained this copper loss and we obtained this core loss. This is also called as iron loss. Core loss or iron loss. Okay. Now what we are going to do is we want to fix this value. So our rating of the machine is, overall rating of the machine is 3 kVA. Okay. So the rating of the machine is 3 kVA and the current rating is 13.6 rated and the voltage rating is 230 volt rated. Now what we are going to do here, the overall value, that is VA cos phi, this is the power factor that we have written it here. So this V into I, we have written it as kVA rating. Now what we are going to do, we are going to fix this voltage value as 230. We are going to fix this voltage value as 230 and we are going to change this current value from 0 to rated. Okay. So suppose, let's say that I want to find the efficiency of the transformer at 10 percentage, 10 percentage of the, I mean, overall loading. So 10 percentage means overall current is 13.6 and the 10 percentage of this current is 1.36. What I'm doing, I'm keeping the voltage as fixed. After I keeping the voltage as fixed, I'm going to choose the current rating according to my requirement. So I want to find the efficiency of the transformer at 10 percentage loading. Then this for kVA, what I'm going to do, for V, I'm going to substitute 230, and for I, I'm going to substitute 1.36. Similarly, I'm going to substitute V as 230 here, and current as 1.36 here. Then let's say that I'm going to use a resistive load, so I am considering that power factor as 1. So that is this cos phi as 1. Now, from this expression, the iron loss is constant. Iron loss is constant. I told that from no load to full load, the iron loss or the iron loss or core loss, the iron loss or core loss will be constant. Whereas this copper loss will change according to the current. So the copper loss is equal to I square R, right? So this much current is going to flow through this circuit. So now, whichever the current you are considering, so 1.36 square into this resistance is nothing but the series resistance which we have obtained in the short circuit test, that is R01. So now you substitute this value R01 and you substitute the value of I, then what you can obtain, you can find the efficiency of the transformer at 10% of loading. Similarly, if you want to obtain the efficiency of the transformer at 25% of the loading, then this is 100% of loading, and you just divide this by 4, you will be getting 25% of that loading. So that is, let's say, X current, that is around 3 point something. So I think it is around 3.4. So for 25% of the loading, it is coming around 3.4. Then for that case, you can substitute voltage as 230 into 3.4 ampere, then 10 to the power of 3, power factor is 1. Similarly, for here in the denominator, you have to substitute 3.4 ampere. Then here for copper loss, you have to mention 3.4 the whole square into R01. Now, what we are doing, we are able to find the efficiency of the transformer at any percentage of the loading. Okay, at any percentage of the loading, we are able to obtain the efficiency of the transformer. Okay, so this is going to be an advantageous one, because in order to find the efficiency of the transformer at any percentage of loading, we are not doing the load test directly. Without doing the load test directly, we are able to find the efficiency of the transformer at any percentage loading. Okay, so that is the requirement for the open circuit test and short circuit test. In open circuit test and short circuit test, what we are finding, we are finding the parameters of the equivalent circuit. Other than that, we are measuring the copper loss and core loss. So copper loss in open circuit test and core loss in open circuit test and copper loss in the short circuit test. So those things we are using in this equation in order to find the efficiency of the transformer. Then percentage regulation of the transformer. So what is the percentage regulation is, see, suppose if we are having a transformer, suppose if we are having a transformer, if the current flowing through this path is increasing, that is the secondary current is increasing, that is the load current is increasing, then what happens is the EMF induced on this will be decreasing. Okay, so from no load to full load, the induced EMF V2 will be decreasing. Actually, in another way, you can say that actually the voltage across the load will be decreasing. Okay, so the voltage across the load will be decreasing. Why it is decreasing? Because copper loss is increasing from no load to full load. When the copper loss is increasing from no load to full load, the voltage across this load will be decreased. Also, the induced EMF will also be decreased. Okay, because there is some copper loss on the primary side. So because of that, the induced EMF will also be decreased. Also, the voltage across the secondary terminals will also be decreased. Now, if I increase this much load, if I add X amount of load, then some amount of voltage is going to decrease. Okay, that is what we are going to read it in the percentage voltage regulation. This is percentage voltage regulation. So in percentage voltage regulation, we are going to find the how much amount of voltage percentage, how much amount of voltage in terms of percentage is going to reduce when you are going from no load to full load. When we are increasing the current from no load to full load, that is a 0 ampere to 13.6 ampere, how much voltage is going to be reduced on the secondary side, that is the induced EMF and the uh, load voltage, that we are going to see in the voltage regulation. So already we have obtained this R01, already we have obtained this X01. So from this we just need to substitute the R01 and X01. Then ISC is the current, which is the rated current of that transformer, and open circuit voltage is the 230 that we have to substitute. This is the rated voltage of the transformer. Then X is going to mention that how much amount of current is going to flow. So out, if it is 13.6 ampere, it is the rated current. So if you want to make 1% of the current to flow through this, or 10% of the current flow through this, so 10% means you have to multiply with zero point 0.1. If it is 20%, you have to multiply with zero point 0.2 or zero point 0.2 for this X value. So if you just put X is equal to 0.2, then it will be taking the 20% of the current. Then you can find the voltage regulation of that particular thing. Okay, so here you are getting two parameters. One is cos phi and sin phi. So how we can obtain cos phi and sin phi is from the open circuit test. You can obtain this cos phi. So cos phi is given by power divided by this V into I. So P is equal to VI cos phi for single phase power, that we did not see, but V is equal to P is equal to VI cos phi. So this is what we measured in copper loss. Sorry, this is what we measured in open circuit test. Then you substitute this P here and you substitute the value of V into I. So you can obtain the value of cos phi. Once you obtain the value of cos phi, obviously you can obtain the value of sin phi, because if cos phi is some value, then you can, if cos phi is some X value, you can take the cos to the other side. So cos inverse of X, you will be getting the angle. Then after you find the angle, you can able to find the sin phi. So after you find the sin phi, you can find two currents, that is the current which is in phase with the voltage, and the current which is 90-degree with the voltage, that is magnetization current. Okay, so these things will be useful in finding this. So you can just obtain cos phi and sin phi. Once you obtain cos phi and sin phi, you can substitute this in this equation, and you can obtain the percentage of voltage which is going to vary from no load to full load. So here also, without doing the load test, means physically we did not apply any load, but we are able to find the voltage regulation, also the power efficiency of the transformer, without doing the load test directly. Okay, so that's why we are doing this open circuit test and short circuit test. And the next one is load test. In load test, the same thing we are going to do, but we are going to use load. If the transformer is rated for 1 megawatt, then we are going to apply 1 megawatt of load, and we are going to check the efficiency of the transformer. But in open circuit test and short circuit test, irrespective of the transformer rating, we are not going to supply the complete power rating. We don't need to have a source of 1 megawatt or 1 MVA capacity in order to test our transformer. But in load test, we need to have 1 megawatt, 1 MVA source in order to test our transformer. Okay, if you want to implement, or if you want to test a 1 MVA transformer, then you need to have 1 MVA supply in order to test this open circuit test and short circuit test of the transformer. Whereas in, sorry, if you need to test 1 MVA of the transformer in order to find the efficiency and the percentage voltage regulation, then you need to have 1 MVA source for doing load test. You need to have 1 MVA source in order to do the load test. Whereas in open circuit test and short circuit test, you don't need to have 1 MVA capacity of the source. For testing the same 1 MVA transformer, the capacity of the source need not to be 1 MVA in order to do open circuit test and short circuit test. Here you are able to find the efficiency. Also, you are able to find the percentage voltage regulation. Here here also we are able to find the efficiency, and here also we are able to find the percentage regulation. So if we are able to calculate both in open circuit test and short circuit test, also with the load test, Why do we need to have two tests? So here, when we find the efficiency of the transformer, what happens is we assumed one thing. In this KVA rating, we assumed one thing, that the voltage is 230 and the current is varying. But practically, this voltage is also varying. Okay, practically, if you speak, this voltage is also varying. So we are considering it as a fixed voltage. This is not correct. This is an assumption that the voltage is maintained constant as 230, but it is not going to be constant. It is not going to be constant. That voltage is going to change. Okay, so that's why we need to have two tests. Other than that, this is not going to give very accurate value, because we have certain assumptions when we are making this approximate equivalent circuit. So we are not going to get the accurate efficiency or accurate voltage regulation using the open circuit test and short circuit test, because when we are preparing this equivalent circuit, we made several assumptions in order to prepare that equivalent circuit. So when you are going for load test, you can obtain the efficiency and percentage voltage regulation in more accurate manner. Okay, so here the efficiency whichever you are calculating is more accurate than the load test, but only drawback here is you need the power capacity of the source should be equal to the power capacity of the transformer. Okay, so once you are doing the load test, whatever you will be measuring is, you will be measuring the primary voltage, primary current, primary voltage, primary power, then secondary current and secondary voltage. Then once you know this, this is, we are considering a resistive load, you can just multiply voltage into current, you will be getting the power, that is P is equal to V into I, that you will be getting VA cos phi is 1. So that we will be getting. So from this, the primary current you are measuring, secondary current you are measuring, then primary power you are measuring, also you can calculate the primary power, then secondary voltage you are measuring and the secondary current is measuring, from that you are measuring the secondary power. So there is some primary power. This primary power is supplied by the source. This primary power is supplied by the source, and the secondary power, that is W is SEC. This is primary. So WSEC is supplied to the load. That is, this is the load power. So what we are doing, how much power it is coming inside, how much this is X power is coming inside. Here in the load you are consuming Y power. Okay, so there is a difference in X and Y. Okay, X power is taken from the source, but the same X power is not supplied to the source. So there is a difference in value between X and Y. So you are getting percentage efficiency can be given by output, that is this Y is the output, divided by input into 100 percentage. So there is a difference between your input and output. So your efficiency will always be less than 100, because your input is always higher when compared to the output. So since the input is higher than the output, always your efficiency will be less than 100 percentage always. If you say that I got efficiency as more than 100 percentage, then it is very easy to say that you have done something wrong. Okay, there may be some calculations mistake, the efficiency cannot go beyond 100 percentage at any cost, even it cannot come to 100 percentage also. So the efficiency will always be lesser. Okay, now we have applied the load directly. With that applied load, what we have obtained, we have obtained the primary power, that is, we have measured the primary power and we have calculated the secondary power. So secondary power divided by the primary power into 100 will be giving the efficiency of the transformer for any particular loading. Okay, so that we are going to do in this. Just a minute, it got stuck. So in this, output power divided by this input power. So output power is the secondary power which you are calculating, and this is the primary power which is measured. So into 100 will be giving the efficiency of the transformer. So now here, this is going to be the percentage voltage regulation. So the percentage voltage regulation with the load test, you can give the relation as V secondary at no load minus V load. So at 0 ampere, at 0 ampere, when you are not having any load, then that is considered as no load condition. At that time, the secondary voltage will be 230 volt. Will be 230 volt. Then this is also V secondary at no load. This is also 230 volt. So when you are applying load, what is the voltage across in the secondary terminal, that you can just substitute. Then you can find the percentage voltage regulation. So here the percentage voltage regulation should be very much lesser for a good transformer. If you want to go for a good transformer, then when you are increasing the load, the change in voltage on the secondary side should be very much lesser. So if the rated is 230, so when you are increasing from no load to full load, generally you cannot have a voltage which is going less than 10 percentage of it. 10 percentage of it. So maximum you can be having 230 minus 23, you may be getting that, but even that is also not good. You should be having a percentage voltage regulation generally which is less than 10 percentage. Okay, so if you are talking about a very good transformer, then efficiency of the transformer should be very much higher. Then if the efficiency of the transformer is very much higher, then the percentage regulation should be very much lesser. So it says that even when the load current is increasing, the secondary voltage is not changing much. Okay, so if the percentage regulation is lesser, then the transformer is very good. Okay, so if you have any doubt in this transformer, you can ask me now. We have completed this transformer unit, that is the fourth unit we have completed here. So if you want to ask anything, you can ask. If you have anything to ask in this transformer, you can ask. If you have any doubt in this open circuit test and short circuit test, then you can ask me, else let me proceed further. Okay, if you do not have any doubt, let me continue with this delta connection of the three-phase circuits, which I told that I will be taking a recorded class. So I have 10 more minutes. I will be completing this. I will be able to complete this in this 10 minutes. So in the third unit, we had seen about star connection. In that star connection, we have seen the relations between the line voltage and phase voltage, line current and phase current. So that we have already seen in star connection. We did not start the delta connection. So the star connection means you will be getting three terminals which is connected at the same point. So in delta connection, you are having three things. You are having three phases. In that, each phase is connected to another phase through one winding. So this is connected like this, and this one is connected like this. So this is one terminal, this one terminal, and this is another terminal. So here three connections. The AB you can consider. This is CD. This is AF. Three phases you are having. So you are having one connection here. You are having another connection here. Okay, this is R phase, this is Y phase, this is B phase. Okay, so you're having three phases, R, Y, and B. R phase, Y phase, and B phase. So you can have terminal 1 of R phase and terminal 2 of Y phase. So similarly, you can have all the terminals like this. Then in delta connection, what we are doing, we are connecting the end of this one terminal to the starting of this another terminal. So in 2, we are taking it to this one. From this 2, we are taking it to this one. Then from this 2, we are taking it this to this one. Okay, so end of the terminal is connecting to the starting of the another where my screen is visible to you.
Yes, sir.
Yes,
It
sir.
is visible.
Yes, sir.
Okay, so in delta connection, you are having three phases, In star connection also you're having three phases R, Y, B. So you can name like one, two terminals for all the phases. So here also you are having two terminals for all the phases. Okay. So this R, Y, B, this is R, Y, B. So in delta connection, what we are doing, we are taking the second terminal of one phase and we are connecting to the first terminal of the second phase. So similarly, this is second terminal of the one phase and we are connecting to the first terminal of the another phase. Similarly, you are taking the second terminal of this B phase and connecting to the R phase. So now what we are doing, we are connecting like this. So this is for the delta connection. For star connection, you are short circuiting or we are short circuiting all the second terminal. So or we are short circuiting all the first terminal. Okay, so we are taking wire like this. This is what our star connection is, and this is what our delta connection is. Okay, each are having its own advantage. Why do we need to use it? That each are having its own advantage in power system, that is in electrical point of view. Okay, so like that, I told the delta connection is connected like this for three phases R, Y, and B. This is Y and this is B. So now here, one thing you note down here is, if you take one phase, so one phase, this is one phase, so this is R terminal and Y terminal. So the voltage across these 2 points and the voltage across this point, let's say R1 Y1. So R1 Y1, here in delta connection, R1 Y1, the voltage across this R1 Y1 is considered as phase voltage. The voltage between this R1 and Y1 is considered as phase voltage, and the voltage between this VRY, this is one line and this is another line. So the voltage between VRY is considered as line voltage. So the point in delta connection is VRY is equal to VR1 Y1. There is no difference in voltage. So in delta connection, the phase voltage is equal to the line voltage. In star connection, the phase current will be equal to the line current. In delta connection, the phase voltage is equal to line voltage. The phase voltage is equal to line voltage in delta connection. Okay, so that's why I have drawn it here like this. Then here this the voltage across this two terminals, so across this source, that is VBR, is considered as phase voltage. Similarly, the voltage across these two terminals, that is across this source, that is phase voltage. Okay, if there is a load here, then it is also a phase voltage, but it is the voltage across the phase. Here it is the source, so it is a phase voltage across the source. Okay, so here in any phase, the phase voltage will be equal to the line voltage. So the magnitude of phase voltage will be equal to the line voltage. So you can see here that at any node, we can apply KCL. At any node, we can apply KCL because there is some current is going to flow through this path. I'm just drawing it randomly. So there is some current is going to flow through this path. Then because of this, you can apply KCL at this node. So if you apply KCL at this node, you will be getting some current as outgoing and some current as incoming. So for this particular source, for some time instant, you can consider that the current is coming out of this source. Then current is going to be divided in these two paths. Okay, so from this you can write IBR is equal to outgoing currents as IRY plus IR. So what is this IR? This IR is the line current and these two are phase currents. IR cap, which is represented in the capital letter, that is line current, which is represented in the small current, letter, that is line current. So here you can see one thing clearly, that I have assumed current direction as the current is entering the positive terminal for all the sources. You can consider that the current is considered as positive terminal for all the sources. So from that I have started writing the equation. So once I started writing this equation, so I can apply KCL at any node. So I have three nodes. I am applying KCL at all the nodes. So for this first current, that is IR, you can have the current flowing through here is this is in this path. So here there is some current which is incoming and there is one current outgoing. So this is this current is outgoing and this current is outgoing. So IR plus IXY, IRY is equal to small IBR. So what we need IR. You just take it to the right hand side. You will be getting minus IRY. Okay, so that is what I have written here. Similarly, for this phase, that is IYB. So you are having, okay, this is negative terminal. So you are having current which is flowing through this path. So here there is some current which is outgoing, and there is some current which is outgoing to this node, and there is some incoming current. So from this you can write IRY is equal to IY plus IYB for this particular node. Okay, IRY is the incoming current that I have written. Then IY is the outgoing current. This is capital Y. So that is the outgoing current. Then this IYB is also the outgoing current. So we need IY. You just rearrange this equation. We will be getting this IY is equal to IRY minus IYB. So similarly, for this node, you are having three currents. IBR is the current which is going out, and IYB is the current which is coming in. Then IB is the current which is going out for this particular node. So if we apply KCL for this node, we will be obtaining this equation. IB is equal to minus IBR plus IYB. So now you understand one point. As I said before, whichever the current which is flowing into the source, that is considered as phase current, and the voltage across the source is considered as phase voltage. So that I have represented here. The current which is between this thing, IRY, it is mentioned as capital letter. You can consider it in small letter, IBR and IB, small b. So these are phase currents. The currents which are here, that are considered as line currents. Okay, so here one thing you note down: in delta connected system, phase voltage is equal to line voltage, as I told before, but the phase current is not equal to line current. The line current is not equal to phase current, because it is very much understood from this figure. This is the phase current, that is IBR. So this IBR is the phase current and this IR is the line current. IBR cannot be equal to IR unless the current flowing through this is zero. Okay, so you understand that the line current is not equal to the phase current in delta connected system. Okay, so now we will be seeing the relations. So here, for this particular phase, here we have written it from load point of view. Same thing I have written. This is from the source point of view. This is from the load point of view. So if you are having a source, you should be having a load. So I am just connecting these terminals like this. Y and this B. So some current is coming out of the source, that is entering the load. Some current is coming out of the source, that is entering the load. So that is, it is coming here. Now some current is coming here and that is going to flow through this windings. So this is, you can consider like R, Y and B. Okay, this is B terminal. This is B terminal and this is Y terminal. Okay, now we wanted to find IRY. IRY is the current which is going to flow in this particular phase. So there is some voltage. The voltage across the terminal is VRY. This is the phase voltage. So now we are going to divide it by the phase resistance. VRY divided by IRY will be giving the current. VRY, we are considering it as line voltage angle 0 degree. So here you can consider that line voltage and phase voltage are having the same magnitude. For our phase, we are taking VL angle 0 degree. All the magnitude are same. And for Y phase, we are taking VL angle minus 120 degree. And for B phase, we are taking VL angle plus 120 degree. So these three things are there. So that we are going to consider here. So VRY is equal to VL angle 0 degree divided by VRY. VL divided by VRY angle 0 degree. Okay, now in this VRY is also having some angle. So when you want to find the magnitude of this, you have to subtract, you have to find the angle of this, let's say theta 1. Then you have to take it to the numerator. You will be getting 0 minus theta 1. This is for the voltage, this is for the current in the R phase or Y phase. Now there is for other current also. So the current flowing through this path can be given by voltage across this phase divided by that particular impedance. Similarly, the current flowing through this path can be given by the voltage across this phase and divided by the impedance. Okay, so that you can calculate. So when you are finding the impedance magnitude, then some angle will be coming. That angle you have to take it to the numerator. So this is for finding the current in the delta connection. Okay, so we can see this phasor diagram in the next class, or I will be sending the recorded videos for this. So if you have any doubt, you can ask, else you can leave the meeting.
Okay, Maria चलवा Maria
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.